I definitely feel like I'm not the most qualified person to go through a gravity tutorial, but I'm equally recording this for myself so that I remember. And please correct me if I'm wrong in the comments. But I suppose a lot of older geophysicists feel frustrated that younger geophysicists push buttons and don't always look at their data. So I thought I better look at my data before I get moaned at. And so I've really just put together some screenshots of the data that I've got out with the main aim of just seeing, does it make sense? And so I've just put this up here, and I didn't put a reference. I apologize for it. I think it might be in Mark Denti's book. I'm hugely apologizing. But just the different gravity corrections that we need. But equally the equation, because I know people are going to moan that I've put minuses everywhere, and actually it depends. Sometimes it's minus or plus. So, I mean, you're getting your observed gravity data here. You're applying your latitude correction, which should be plus if it's in the south and minus in the north. I assume this is because latitude is minus in the south, so that's why it's going to be opposite. Then you've got plus or minus for your free air correction, and so you're adding the correction if it's above the datum, and I assume this is because the higher up you are above your base station, the further you are from the center of the earth, so the weaker the pull of gravity, hence the fact you have to add the correction, whereas as you're going down under your base head towards the earth, there's a stronger pull of gravity, so you have to minus. But it could be very wrong. And then it's the opposite for the Bouguer correction, because you've got so I mean, you're minusing if you're above the datum because you've got a larger slab of rock underneath your feet. And then the terrain correction, I wasn't 100% sure about why you add it. But yeah, this is the equation you have to be aware of. So yeah, signing out with our data. This is the data on the left-hand side. These numbers here are the days on which it was collected. So you can see 27th was in the middle, then they did the 28th, 29th, and 30th. And please note that all these points here are the data points, but there is one data point over here and over here. So there's no data points covered in this big pink anomaly. And then we've got the elevation data. So, I mean, I would assume you should actually just delete these two outliers to get a better grid and less gridding effects, or you could mask your grid. And then here's your elevation data, and you can see pretty decent elevation changes. I mean, if you look at the reds here, well, it's not huge. So, I mean, you're looking at, 5 meters elevation change is quite massive. And the big thing to note is there's actually no readings here in this blue region. Your background readings here are your greens. So, I know that is pretty huge. That's a 50-meter elevation change. And so what we did originally was we calculated a drift correction. And you can see here's the original gravity, here's the drift correction, which really wasn't that big a value. And it's quite easy to see this was the 27th over here, the 28th. And the 28th, you can see this increase over the day. And then 29th and 30th up here was this blue. So you can see now why you need to separate it out day by day. And then this last value here is the original gravity minus the drift. But you can see here these values shoot up to 900,000, whereas they were originally 6,000. And I think that links with this instrument height correction, because you had to choose the latitude column, I think it was. Let's just look down here. Yeah, I feel like it had a latitude column. So I think it's linking with the shape of the Earth, possibly, that's why it's getting so big. But this wasn't so serious, because in the next step we did our latitude correction, and you can see our latitude correction itself was very big, this 900,000. And so as soon as we took it away from our gravity drift correction, we got down to smaller values. So this, and you can see the latitude correction looks weird, but not actually, because you're expecting it to be regular with latitude. Okay, and then the next thing we did was to look at our repeat values. So on the left here was the gravity data. Middle here is the mean gravity data. So any repeat values here the mean was calculated, and they don't look too different from each other. And then on this right-hand side is the mean minus the original data. And you can see the values are anything less than 0.015. So pretty good data. And these were the stats at the bottom that I took a screenshot of. Then we moved on to the terrain correction, which I definitely feel the least comfortable with, because I have not worked with it much. And you can see elevation on top here, and on the right hand side here you can see a DEM of the area. And if you follow my mouse to this little block in the middle, this is the elevation area on the DEM. So you can see the DEM covers a much larger area than the elevation, this localized elevation data, which I'm assuming they got just at the gravity stations. And so this is a screenshot of the menu we used, and so we had to put in elevation and the DEM, and we went to a distance of up to 50,000 kilometers, 50 kilometers around this elevation grid. And so also down here, I've just zoomed in a bit so you can see where this elevation grid is on the DM. And then this here on the right-hand side is a screenshot of the area the DM's covering. You can just see the resolution difference between the two. But in general, you've got a high elevation here, which is shown by these reds, going down, but I'm not sure it's as we said, this blue here, there's no actual data points inside of it. So that's a bit troubling that it will affect the terrain correction. And then here's our terrain correction over here, gridded up. And at the bottom here, I've got the elevation data in purple and the terrain correction in blue. And they are anti-correlated over here. You can see there's a high terrain correction with a low elevation. But over here, it's not really working as well. So definitely a need to go and investigate this a bit more. Okay. And then we took, we did our free air correction. And remember, it was in a menu by itself. It didn't actually include the terrain correction for it. That actually comes in the next step with the Bouguer. And so this is our free air correction. And I put the elevation data up here so you can really see how well the free air and the elevation correlate, because, I mean, it's completely linked. And then the last step here, I've put on top the simple Bouguer, and the bottom was the complete Bouguer. And remember, we read in the tutorial that it had to do, instead of it being a slab for the Bouguer correction, it actually was, oh, now I've completely forgotten, but it takes better account of the terrain for the complete Bouguer. And so in this last window here, we've got a terrain correction, the free air correction, and the Bouguer correction. And it looks like this. And in the last step, we'll kind of compare all of our grids. So here's the original and the elevation. We do a drift correction, not too much changes because the values of the drift are quite small. We do the latitude correction. Lots changes because the latitude is linked with the shape of the Earth, but actually the change due to this latitude correction from north to south is not that big. And again, the gravity data that's been drift corrected and latitude corrected looks pretty similar to the beginning. Then we've got our terrain correction, and I didn't actually look at the scale, but the scale's not big. I mean, it goes up to 0.2, which is not small, but it's, yeah, it's, I suppose we'll see now. The free air correction here, it's anything ranges from 142 to 148, which again, big, I suppose, for gravity, and strongly follows the elevation. And so then you're kind of removing these two from this original database to come up with this final Bouguer correction. And here I've got a simple Bouguer anomaly, so you can see I said a slab terrain correction, the free air, and the Bouguer correction. But if you look back at the two, I mean, the data is over this region over here. Not too much is changing. I suppose something we should actually be looking at is the actual value change across the two. So, but I mean, this big blue anomaly here, which is linked with this topography over here, has been corrected out of it. So I'm just going to pause for a sec. Okay, so I could make sure that I wasn't talking rubbish. On the left-hand side here, I've got the gravity data gridded up. So this is the original data. And on the right-hand side, I've got the simple Bouguer correction gridded up, and I've put the scale bar. And so you can see on the left here, the original data has got a range of about 12 milligauss, going from the pink here down to the blue, whereas on the right, the simple Bouguer has only got a range of 1 to 2 milligauss. So you can see how much has been removed from it.